In this video, we will be continuing our look at the language of organic chemistry, focusing on the specific use of arrows. Often it can be very helpful to think about organic chemistry as a foreign language because there are many symbols that you need to know, like vocabulary words. So the arrows in organic chemistry are different and they have specific meanings and they are not interchangeable. So it's very important that you can distinguish the different types. So this one, for example, is a reaction arrow, whereas this next one would be a reaction at equilibrium. So if a reaction is going both in the forward and the reverse direction, that's what we're talking about there. This double-headed arrow, notice we're not talking about an equilibrium arrow. Here we've got the heads on both ends. This one is a resonance arrow. This one we won't be using for a while, but this is called a retrosynthetic arrow. There are a few others that you probably saw in Gen Chem that we have used already, and one of them is a bond dipole, as well as the molecular dipole. In addition to these arrows, there's a set of curved arrows that have very important meanings, and these are really important as we think about reactions. Well, the first two at least. So the curved arrow with a double barb, as opposed to here, notice there is just a single barb. So the curved arrow represents the movement of a pair of electrons. This is the driving force behind reactions. So reactions are all about the movement of electrons. And so by using curved arrows, we can describe the mechanism of a reaction. So then this one where it is a single barb, and again, what we're looking at is not having 1, 2, but just having 1. Here we're talking about the movement of a single electron. Now the next pair of arrows, this is a double barbed with a dash line, which would be similar to this one. And this is a single barbed with a dash line, which is related to this one. And these are ones that I like to use as we are drawing different resonance structures. We're going to talk more about resonance in the next video, and we're talking about an imaginary movement of electrons. So I like to use a dashed arrow rather than a solid arrow to be able to distinguish the imaginary movement of electrons within resonance as opposed to the real movement of electrons within a reaction. So this one refers to the movement of a pair of electrons. And then this one represents the movement of a single electron. Again, the movement is in quotes because it's not real movement, it is an imaginary movement, which we'll talk about in the next video. So some of these arrows you have probably seen already in general chemistry. Some of them are probably new, but they are incredibly important for being able to communicate in the language of organic chemistry. In the rest of this video, we're going to focus on the curved arrows, and I want to show you how these can be used. Let's change topics for a moment and we're going to talk about acid-base reactions. So if we have an acid such as hydrochloric acid and it reacts with a base such as sodium hydroxide, these can react together to form water and sodium chloride. Now the net ionic equation, this means that we are ignoring counter ions that aren't involved. So we ignore the sodium and we focus on hydroxide plus HCl reacts to form water plus Cl minus. Now, if we look at this reaction in a little more detail, what we want to focus on is how this reaction actually occurs. So notice we're starting out with hydroxide and we're ending up with the hydroxide connected to a hydrogen, and so that hydrogen must be this hydrogen. This pair of electrons remains on the chlorine as an additional lone pair. So how does that happen? Well, we can represent this by focusing on the fact that this pair of electrons would be shared with this hydrogen. I'm using the double barbed arrow because it is a pair of electrons, and this means it's forming a new bond between the oxygen and the hydrogen. And then at the same time, these electrons are going to move onto the chlorine. So our hydroxide is now connected to the H that used to be connected to HCl, and the Cl is still connected to its 3 lone pairs it originally had, but now this pair of electrons exists on the chlorine as another lone pair, and chlorine has a negative charge. So here we have an example of an acid-base reaction. Throughout this year, we're going to talk about a lot of different reactions. And always, reactions are driven by or caused by the movement of electrons. Keep in mind, the electrons are way on the outside of an atom, and they are able to move. Okay, the nucleus can't move. This hydrogen cannot move over to the base. The base has to use its electrons to grab it. So reactions are driven by the movement of electrons, and curved arrows are used to represent this movement of electrons. So why do we want to do this? We want to indicate the movement of electrons in part so that we can think about electron bookkeeping to make sure that we have the correct number of electrons, what we started with, what we ended with. And it also represents the mechanism. How does this occur? What is the flow of electrons? Where are the bonds breaking? How are the bonds forming? But another way to think about this is that by using these arrows, this gives us a very efficient shorthand to be able to describe what's happening. If I wanted to describe what's happening without using arrows, I would have to say that a lone pair of electrons on the oxygen of hydroxide is used to form a new covalent bond with the hydrogen nucleus of hydrochloric acid. At the same time, the pair of electrons that used to be shared between the hydrogen and the chlorine in HCl moved onto the chlorine as an additional lone pair of electrons, which resulted in the formation of water with a new bond between the oxygen of hydroxide and the hydrogen of HCl, and a new lone pair that used to be the shared electrons between the hydrogen and the chlorine. Now, that's a whole lot of words to be able to describe what we see here with our green arrows. So being able to use curved arrows correctly can deliver a lot of information in a very efficient way. Let's continue to think about curved arrows. One warning that I want to give you is that depending on how an arrow is drawn, whether I'm using ChemDraw, whether I'm drawing it by hand, whether it's from the textbook, moving a pair of electrons could be represented by a double barb that's open, a double barb that is closed, or a double barb that is closed and filled in. Moving one electron could be represented by a single barb that's open, a single barb that's closed, or a single barb that's closed and filled in. So these mean the same thing as each other. These mean the same thing as each other. So please keep that in mind. Another important aspect of the curved arrow is that we're always talking about the origin of the arrow is at the original location of the electron, and the arrow points to the final location of the electron, where it starts, where it ends. So it's possible that the original location could be a lone pair of electrons. It could be a double or triple bond. Or it could be a single bond, but that's not as common. In terms of the final location of the electrons, it could end at an atom, which results in a new bond. It could be on an atom, which results in a new lone pair of electrons. Or it could be at a bond, which gives a new double or triple bond. So for example, let's say we have A with a lone pair reacting with B, and our arrow goes from here to here, resulting in a new bond. Another example would be if we have A and B, and we have a lone pair on A. If the arrow starts at the lone pair and goes to the bond, then we are ending up with a double bond between A and B. So in both of these cases, we're starting with a lone pair. In the first case, we are ending at the atom, so this is a new bond. In the second case, we're ending at a bond, which gives us a double bond. So we're going to see many reactions that involve starting with a lone pair, ending in any of these locations. We're going to see a number of reactions that involve starting with a double bond and ending at these various locations. So keep this in mind each time we're looking at a reaction. Now this slide includes an animation in PowerPoint. It's not going to show here, but I will post this on our Canvas site. We need to remember that curved arrows represent the movement of electrons in reactions. So once again, if we have hydroxide reacting with HCl to form water and chloride, we can draw a curved arrow showing this lone pair of electrons moving here to form a new covalent bond with the hydrogen. And so this is what used to be the lone pair. It's a new covalent bond between the oxygen and the hydrogen. And then this orange line, this pair of electrons that used to be shared between the hydrogen and the chlorine, these moved on to the chlorine, and so this is a new lone pair. Every time we are thinking about our electrons and thinking about the movement of electrons, I want you to think about the early things that we talked about in terms of atomic structure. Right, we've got the nucleus is really, really small, and then the electrons exist in orbitals, not in a perfect orbit. It's not a solar system. It is orbitals, which you can think of like squishy clouds, because we're thinking about the probability of the location of the electrons. So this line means there is a pair of electrons in between these two atoms, so we can think of it as if it's this cloud where the electrons are likely to exist. I'm not showing the blue lone pairs, but the green lone pair, that could be a cloud that exists over here. Hydrogen and chlorine, this bond is also a cloud. Now, as these electrons move over here to grab the proton, we want to think about this cloud stretching out to grab the hydrogen. And then this cloud stretches out as this bond is breaking. So whenever you are seeing arrows, I want you to try to think about squishy clouds and that it's this movement of the clouds that is actually happening in the reaction. Based on the little bit that we've talked about curved arrows, you now have the tools that you need to be able to focus on a couple of mechanistic steps in the hydrolysis of an ester. So we haven't even learned yet, what is an ester? What does hydrolysis mean? This is a reaction that we're going to talk about second semester, but we can still demonstrate some important information about this. So in the first case, we're asked to add curved arrows to trace the movement of electrons. So this is what we're starting with, and this is what we end with. Now this looks very different, but let's try to figure out which atom is which. So this carbon, this carbon, this oxygen, this carbon, that would be this carbon, this carbon, this oxygen, this carbon. And then the hydroxide is now connected to this carbon. And here we have a double bond to the O, and that same carbon is now single bonded to the O. The first thing we need to do is figure out which atoms in the product correspond to which atoms in the starting material, but then we can start to see some of the changes that have happened. Now I'm going to erase these colors so that we can just focus on the reaction as written. So the hydroxide oxygen is now connected to this carbon, so that's this carbon. So we can represent that movement of electrons where this lone pair is shared with this carbon, forming a new covalent bond between this oxygen and this carbon. So that's going to result in this bond right here. At the same time, while this bond is forming, that would give us 5 bonds to carbon, so that can't happen. So one of these pairs of electrons must move onto the oxygen. Notice we're starting out with 2 lone pairs, we're ending up with 3 lone pairs. So these electrons are moving up onto the oxygen, and this is where they exist now. So even though we don't know anything about this reaction or why it happens or what type of reaction it is, we can still follow the movement of electrons to see the changes that happened. And we can use curved arrows to demonstrate that. Now here's another example. Write the products of the reaction using the curved arrows to guide your answer. So once again, we don't know anything about this reaction, but we can interpret the arrows. So this says that this pair of electrons, this is where the arrow starts, so this pair of electrons is going to move toward this hydrogen, and so it forms a new bond between the oxygen and the hydrogen. At the same time, this pair of electrons that used to be shared between the hydrogen and the oxygen move onto the oxygen. So I think we can do this. So we have our CH3 connected to our C, connected to our OH, connected to our OCH3. No changes are happening here. This oxygen is still connected to these 2 lone pairs, but now there is a new bond to a hydrogen. So this pair of electrons is this pair of electrons, and this hydrogen is this hydrogen. But we're not done, because what we have left is hydroxide, where we started out with 2 lone pairs. We still have those 2 lone pairs, but now we have a new lone pair. And this oxygen will have a formal charge of -1. So this pair of electrons is now this pair of electrons. So as long as we remember that the curved arrows represent the movement of electrons, and as long as we remember that we always start our arrow at the original location and point to the final location, then we will be able to communicate a lot about organic reactions.